Ever wondered how police radar guns can accurately catch speeding vehicles from hundreds of meters away? In this episode of Consumer Times, we dive deep into the fascinating world of speed measurement technology. Discover the engineering brilliance, metrological precision, and real-world applications of radar equipment that keeps our roads safer. From the Doppler effect to calibration standards, we break down everything you need to know about this critical traffic enforcement tool. Whether you are a curious driver, an engineering enthusiast, or simply interested in how technology impacts daily life, this video reveals the science that's been hiding in plain sight on our highways. Hello and welcome to Consumer Times. Today we will talk about speed enforcement technology that has become an indispensable part of modern road safety infrastructure, and at the heart of this system lies one of the most elegant applications of physics and engineering: radar speed measurement equipment. While most drivers have encountered these devices during their journeys, few truly understand the remarkable science and precision engineering that enables a handheld device to accurately measure a vehicle's speed from hundreds of meters away. The story of radar speed guns is not just about catching speeders, it's about how scientific principles, metrological standards, and engineering innovation converge to create a tool that has fundamentally changed traffic enforcement worldwide. Before we deep dive into the subject, please give your valuable comments, like, share and subscribe to motivate us. The significance of accurate speed measurement technology cannot be overstated in our contemporary society. Road traffic accidents remain one of the leading causes of injury and death globally, and excessive speed is consistently identified as a primary contributing factor. According to various traffic safety studies, even small reductions in average vehicle speeds can lead to substantial decreases in both accident frequency and severity. Radar speed enforcement equipment serves as both a deterrent and a detection mechanism, encouraging drivers to maintain safe speeds while providing law enforcement with reliable evidence when violations occur. Beyond simple enforcement, the data collected from these devices helps traffic engineers understand traffic patterns, identify dangerous road segments, and make informed decisions about infrastructure improvements. In essence, speed measurement technology has become a cornerstone of modern traffic management systems, contributing to the broader goal of creating safer, more efficient transportation networks. The engineering behind radar speed measurement devices represents a fascinating application of fundamental physics principles, particularly the Doppler effect discovered by Austrian physicist Christian Doppler in 1842. The word radar itself is an acronym for radio detection and ranging, and while originally developed for military applications during World War II, its adaptation for civilian speed measurement showcases the versatility of this technology. The basic principle is elegantly simple yet scientifically profound. When electromagnetic waves strike a moving object and reflect back to their source, the frequency of the returned waves shifts proportionally to the object's velocity. If the object is moving toward the radar source, the reflected waves are compressed, resulting in a higher frequency. Conversely, if the object is moving away, the waves are stretched, producing a lower frequency. This frequency shift, known as the Doppler shift, is precisely what radar speed guns measure and convert into velocity readings. Modern radar speed guns typically operate in specific frequency bands allocated by regulatory authorities, most commonly the K-band around 24 GHz and the Ka band around 34 to 36 GHz. The choice of frequency involves careful engineering trade-offs between range, accuracy, beam width, and susceptibility to interference. Higher frequencies generally provide better resolution and more compact antenna designs but may have reduced range and can be more affected by weather conditions. The transmitter component generates continuous wave or pulsed electromagnetic radiation at the chosen frequency, which is then directed toward the target area through a carefully designed antenna system. When this radiation encounters a moving vehicle, it reflects back with a frequency shift proportional to the vehicle's speed. The receiver section captures this reflected signal and compares it with the original transmitted frequency. Sophisticated signal processing circuits then calculate the frequency difference and convert it into a speed reading using the mathematical relationship derived from the Doppler equation. The metrological aspects of radar speed measurement equipment are crucial to ensuring that the readings can be trusted as legal evidence in traffic enforcement proceedings. Metrology, the science of measurement, demands that any measuring instrument used for regulatory purposes must meet stringent accuracy standards, undergo regular calibration, and maintain traceability to national or international measurement standards. Radar speed guns are typically required to have an accuracy of plus or minus 1 to 2 miles per hour or 1 to 2 kilometers per hour, depending on the jurisdiction. This level of precision must be maintained across varying environmental conditions, target distances, and approach angles. To achieve and verify this accuracy, manufacturers incorporate self-test features and calibration routines into their devices, often using tuning forks that vibrate at frequencies corresponding to specific speeds when struck. These tuning forks serve as portable reference standards, allowing officers to verify proper operation before and after enforcement sessions. The certification and verification process for radar speed equipment involves multiple layers of oversight. Manufacturers must demonstrate that their devices meet specifications established by standards organizations and regulatory bodies. In many countries, independent testing laboratories evaluate new models before they can be approved for law enforcement use. Once deployed, individual units require periodic recertification, typically annually, by qualified technicians using traceable calibration standards. This metrological chain ensures that every speed measurement can theoretically be traced back to fundamental physical constants and primary standards maintained by national metrology institutes. The legal admissibility of radar evidence depends heavily on this documented calibration history and proper operational procedures, making metrology not just a technical concern but a legal necessity. Advanced engineering features in modern radar speed guns address various practical challenges encountered in real-world traffic enforcement. Target identification algorithms help distinguish between multiple vehicles in the radar beam, identifying which specific vehicle's speed is being measured. Direction sensing capability allows officers to measure speeds of vehicles traveling in either direction, and some models can simultaneously track multiple targets. Range gating features enable operators to focus on specific distance zones, reducing interference from nearby objects. Digital signal processing techniques filter out environmental noise and clutter, improving measurement reliability in challenging conditions such as heavy traffic or adverse weather. Many contemporary units also incorporate digital cameras that capture photographic evidence linked to each speed measurement, creating comprehensive documentation for enforcement purposes. The practical deployment of radar speed measurement equipment requires careful consideration of operational factors that can affect accuracy and reliability. The angle between the radar beam and the vehicle's direction of travel, known as the cosine angle, can influence readings if too large, although this typically results in underestimating rather than overestimating speed. Environmental factors such as electromagnetic interference from power lines, radio transmitters, or other electronic devices can potentially affect measurements, necessitating careful site selection for enforcement operations. Officer training emphasizes proper technique, including optimal positioning, target verification, and documentation procedures. Understanding these operational nuances ensures that the sophisticated technology is used effectively and that the evidence collected will withstand legal scrutiny. Looking toward the future, radar speed measurement technology continues to evolve with emerging applications beyond traditional enforcement. Automated speed enforcement cameras combine radar sensors with imaging systems and recognition software to operate autonomously. Variable speed limit systems use radar data to adjust posted speeds based on real-time traffic conditions. Intelligent transportation systems integrate speed measurement data into broader traffic management platforms. As vehicles become more connected and autonomous driving technologies develop, the fundamental principles underlying radar speed measurement will likely find new applications in vehicle-to-infrastructure communication and automated safety systems. The engineering and metrological foundations established for traffic enforcement are paving the way for these next-generation applications, demonstrating how a technology developed for one purpose can evolve to address emerging needs in our increasingly complex transportation landscape. Thank you for watching Consumer Times. If you found this explanation helpful, please like, share, and subscribe.